Okay, so welcome to part two of this button slash keypad detect project with Xilinx FPGAs. And today we're going to get into the code. So I have here the button detect module, and that's the state machine that we looked at last time. And so a project description, it's a basic sequence detector, and it looks at buttons that are pressed. So if the correct sequence is pressed and the unlock switch, and I guess that should be enter actually, because that's the button that we had in the state machine. The enter switch goes high, a blue LED will light, and a 392 hertz tone will sound. Now you don't have to have this 392 hertz tone. You can just have the LED, and we'll get into that a little bit later. If you don't enter the correct sequence and you press the enter button, then a red light's going to light and a lower tone, like an error tone, is going to sound. There's no overlap in this state machine, and what I mean by that is some state machines or some sequence detectors in state machines, they have, say, they were made to detect the sequence 1101. Okay, so if you go through and they detect that sequence, and then they do something after that sequence is detected, maybe they output a high pulse or something like that. And then if the next input they receive is a 1, well, then it goes back to, if you ignore these two, the first 3 bits, then we have these, and it looks like we just kind of skipped a couple of states because you'll go back to not the reset state. And so what I mean by there's no overlap is after the sequence is entered, the next state is going to be the reset state. So you have to enter a full new sequence in order to get the indicator. The correct sequence is going to be button 2, button 3, button 1, button 3. And like I said, my FPGA board has 4 buttons: button 3, button 2, button 1, and button 0. Okay, so the first 3, or the most significant in terms of binary bits, so 3, 2, and 1, those are going to be the sequence buttons, and button 0 is the enter button to see if the sequence is correct or incorrect. File name, version 1.0, first version of this guy. And let's get into the code. So first of all, I have these inputs. I'm using a Moore machine. So I have a clock right here because the way I set up this Moore machine, I think, well, there's definitely a few ways to set up Moore machines, but you need a clock. You can just have different combinational blocks set up different ways. My clock is going to be running at 125 megahertz. That's a system clock on my RDZ710 FPGA board from Xilinx. Well, it's a SoC actually with FPGA fabric. We have the inputs 3 down to 1 button. So those are our sequence buttons, right? And then we have an asynchronous clear, which is going to be active low. We have the enter input, which will be mapped in my XDC file to button 0. XDC file is one of the constraints files that we're going to use in Vivado. We have an output blue, we have an output red. Those are going to the LEDs on the board, and then we have this output tone out, right? And so right now I'm going to comment this, and I'm going to comment this, because just in case you're not going to be using that tone out and you're just going to be using the LEDs, this is the code that you're going to want to be using. And I'm going to have this linked to my GitHub page, so I'll put a link in the description. And if you look, you'll go to my GitHub, and where is it? It's going to be, I will send you to this page right here, and the Verilog code is going to be in the source directory. Okay, so there's source sim for simulation. Those are going to be the test bench files, and then constraints for timing and for pins or IO. So I'll send you that page. So you can try out the code for yourself, and it'll include the commented, everything that has to do with the tone is going to be commented. So the default is just the LEDs, and you're going to have to uncomment things if you want to use the tone. Okay, so for the states, I use local parameters. So I use reset, got2, got23, got231, got23, got2313, indicate blue, indicate red. We talked about those last time. Those are all the states that we're going to be using. Registers, we need a register to keep track of the state. We need a register to keep track of how long the red LED is going to be high. We need a red LED time enable, which is going to allow the red LED to become high, and likewise for the blue time enable and the blue time, right? We're going to have those, and I checked the code. It's going to be 1 second, so we need a counter and a register to make sure that those stay high for 1 second. And it says 500 milliseconds, which should be 1,000, not 10,000, 1,000. Nice. Now we get into this is like the next state logic of the Moore machine, and it has the part of the output logic integrated in it, because one way to code Moore machines is, if we look at some images of it, yeah, so right here. So we have next state combinational logic, we have the state memory, and then we have our output logic. And so see how this is a Moore machine, because the inputs, or the output is only dependent on the next state, right? Or the state that it's in, sorry. It doesn't depend on the inputs because we don't have an arrow going from the input to the output logic. So what we're talking about right now is I actually integrated together this state memory and this next state combinational logic and a little bit of the output logic together. So always at the positive edge of the clock. And I did that because I was getting some latches in my code, or in my, when I synthesized, and I didn't want those in there because they weren't making the code act how I want it to be. So as I said, asynchronous clear. So, or I guess it's sort of asynchronous. It happens on the positive edge of the clock, because when I put in the negative edge, so let's say I did something like neg edge clear, and right, Vivado is going to tell me a warning because it says, well, that's not a clock, and it's right. So what I just did is, for simplicity, I just stuck it right here. So it's not technically asynchronous, but it's close because the clock's 125 megahertz. So if clear is low because it's active low, then the state that we're going to want to be in is reset, right? We talked about that last time in the state machine. Now here is the actual state machine implemented with a case statement. So we have our reset, we have got2, we have got2 and all the way down to our default. And I'm going to talk about the default first, and the default state is going to be reset, and we're not going to have anything high. All right, everything's going to be low. The LEDs are going to be low, and there's going to be no tone going. Now we get into the reset state. So what's going to happen in the reset state? Well, if you go back to the video about the state machine, the reset state, we're going to be looking for button 2. So if button 2 is high, we're going to go to the next state, right? Else, if the enter button is high, right, we don't have a complete sequence yet, so we're going to want the red LED to go high. So we're going to enable that counter register, and I'll show you those below. So when this enable goes high, we're going to go down to this always block right here. The top one, this top guy right here, is for the red, and this bottom always block is going to be for the blue. So if the enable goes high, then we're going to count up, and we're going to allow our LED time register to reach 1,000 or 125 million counts. And since my clock is running at 125 megahertz, well, that's going to be 1 second of total counting time, right? So we're going to let it count up. If we go down to the assignments, we're going to assign red to as long as our LED time is not equal to 0. So as long as it's greater than 0, so it's going to be high, it's going to be 1, or if it is 0, it's going to be 0. So basically the red output is going to be high for this amount of, no, it would be high for 125 million counts, right? Because 0 to this number is 125 million counts, or 1 second. So that's what that's going to do. Else in the reset state, so we go if enter is 0, or if button 2 is 0, and we don't care about the other buttons, just stay in the reset state and don't let anything go high. Got to next state. If button 3, because button 3 is the next correct one in the sequence, right? We got 2, now we're looking at 3. If button 3 is high, go to the next state. Else, if enter, we don't have a correct sequence yet, so enable the LED to go high for 1 second, and put the state in the indicate red state. That's indicating that we have an incorrect sequence. It's going to continue on down like this all the way until got 2, 3, 1, 3. And in this state, we're only looking at the enter, right? Because at this point, we have a correct sequence. We're just waiting for the user to press the enter key to see if it's correct. So if enter is high, then we're going to go, and if the enter button is pressed, really, we're going to move into this indicate blue state, and we're going to enable the blue counter, okay? Else, if the enter button is still 0, don't show anything, because it's not a wrong sequence at this point, but it's not a right sequence either. So indicate blue says if blue LED time is equal to 125 million, right? So 0 to 125 million, that's 125 million and 1 counts, right? So when we go down to this counter right here, we can see if it's less than or equal to this number, count up. So technically it's going to be counting to 125 million, which is, if we include the 0, because remember we initialized the register, this RLED time register to 0, 0 to 125 million, that is 125 million and 1 counts. So after that 1 second, whoops, that's indicate red, after that 1 second of count, so 0 to 124,999,999 counts, that's 1 second of counting. The next count, we're going to go back into the reset state. That's like I showed in the last video with the state machine and those delay blocks. That's what this is. So it's delaying until just after that 1 second mark, then it's going to go into the reset state. Else, stay in the indicate blue state. Similarly, or exactly the same actually, is the indicate red state. So we look at the LED red counter and we wait till just after that 1 second mark, and then we go into the reset state. Otherwise, we stay in the indicate red state. Okay, I already went over the default, and I went over these, which are just counting, and I went over the output assignments. So if you're not going to be using the tone, you can stop the video at this point and just use this code. If you are going to use the tone, if you have access to the speaker, and I'm going to show you the speaker if you want to order it. Let's close that down and close that down. It's not the speaker that I'm using, but it's one that will work. You can buy this speaker from Adafruit, I don't know how you say it, but it's just basically it works with Arduino. You know, I think this making sound lesson, you can learn a little bit more about it. Yeah, doing something like this. And yeah, so you can use this. This is the speaker that I use. 1 pin goes to ground and 1 pin is going to be the output, and it makes a little noise. So let's go over how we generate the tone. First of all, you're going to want to uncomment this, right? So we have that comma there, and we have this, whoops. So everything looks okay in our port declarations, right? So we have this tone out. 1 pin for the output of our speaker, or sometimes they're called buzzers. So I'm going to save that. Okay, and now if we go down to pass the case statement, we're going to go to this tone generation. It says uncomment for use. And the things you're going to want to uncomment are these multi-line comments. So you're going to want to uncomment that one and uncomment that one. This is going to declare two registers, the enable for the 392 Hertz tone and the enable for the 110 Hertz tone. It's also going to instantiate this tone module, which is how we generate the tone using PWM and how we select which one we want. There's a couple more things we have to uncomment. If you look at this line under the tone generation, it says also uncomment the statements containing tone enable 392 and tone enable 1110 in the two always blocks below. Okay, so we go down and we're going to uncomment 1, uncomment 2, and uncomment 3, and then that should work fine. And what that's going to do is it's going to put the tone enable high for 1 second of counts and otherwise keep it low. Okay. Same for this one down here. We need to uncomment 1, uncomment 2, and uncomment 3. So same with that one. It's just going to be a higher frequency tone that we're enabling if for 1 second, and anything after, right? Else, if it's 0, then we want to disable the tone. Save that. Let's go look at the tone enable. And I just closed my GitHub because I am foolish. There, that should work. Source. So this is the module that's instantiated inside this module, the button detect module. And I don't love looking at it on the GitHub screen just because some things are formatted weirdly. So I'm going to open it right here. So we have input. We have a clock input that's going to be 125 megahertz. So same as the button detect module, which is acting as our top module. We're going to have the enable 392, enable 110. Those are coming from the button detect module, right? So you can see right here, those are those registers in these always blocks in button detect. Switch back over to the tone module, and we have one tone out. So I have two lower level instances of a couple modules down here and inside this module. So let's go over those. One is the tone generate, and this just uses PWM to generate these 392 Hertz tones and 110 Hertz tones off of a 125 megahertz clock. And so that depends on this number right here. And if you have a different clock, you're going to have to calculate it a different way. So what I did is I just went, let's see, what did I do here? I wish I commented it. I think I did. Okay, this is what I did. So a 392 Hertz wave has a period of about 2.551 milliseconds. So what I did is I took that time, 2.551 milliseconds, divided it by the period of my clock, and that is about 318,857 counts. So I stuck that into the counter, and that's the number we're going to use. We're going to have a 50% duty cycle square wave. So down at the bottom, you can see of this tone generate module, right? We're going to have these output assignments, and they're going to be half of this counter right here, because 50% duty cycle means half, right? And they're going to start low and then go high when the counter. So this is like a compressed else if statement. So if counter 392 is less than 159482, go 0, else go high, right? So it's going to be low for half of the 2.551 millisecond period and high for the second half, resulting in a square wave with a frequency of 392 Hertz, which is just what we need for the buzzer. Similar thing with the enable 110, enable 110. And that's what we have for the tone generate module. The other module instantiated inside the tone module is this tone select. And because we are only dealing with one speaker, we have a ground input to the speaker. Let me show. We have a ground input, and then we have our signal input, right? Well, we only have one input, and we have two tones to generate. So we need a signal to show, or we need a module to select which tone should be outputted. So what I did is I took two inputs, the enables, and I also took the inputs, or I'm sorry, the outputs of this tone generate module. You can see when I instantiate it, I have these two wires, and those are linking up the outputs of tone generate to the inputs of tone select. So AND gates, I used an AND gate. They're high enabled, right? So anything ANDed with 1 is just that thing. So X and 1 is X. So, and then for disable, it's 0. So we're looking at this enable, and I stuck an AND gate in there. And if the enable is high, well then the output is going to be whatever this 392 input is. So if it's 0 and enable into is 1, it's going to be 0. And that's what we want because our square wave is going to alternate between 1 and 0. However, if enable is low, let's say enable 110 is low, an AND gate is disabled when one of the inputs is 0. So if your enable input is 0 or it's low to an AND gate, that AND gate will always be 0 because the truth table of an AND gate shows that anything ANDed with 0 is always 0, right? So that's how I did that, and I added a little OR gate between them. I guess they're not physical gates, but you see what I did in the code. And that's the tone generate module, or tone module with the tone generate instance and the tone select instance. That whole thing, this module tone, gets instantiated inside our acting top level module right here. And then this tone out, the tone out of the tone module gets outputted to the tone out of the button detect module. That's going to be the code, and I hope I explained that well. If you have any questions, you can leave them in the comment section below. Thanks for watching, and I am excited to work on the next part, which is going to show the simulation of this guy. So thanks.